Welcome to the introduction for the course Matrix Theory and Applications. This course will be a full-length course on linear algebra targeted towards engineers. I will draw from a lot of examples, mostly from data science, artificial intelligence, and electronics and communication engineering. By the end of this course, you will have a solid foundation in linear algebra, enough to take follow-up courses including convex optimization and foundations of machine learning. In particular, you should be able to understand algorithms like principal component analysis for dimensionality reduction, page rank for search, and SVD and its variety of applications in signal and image processing by the end of this course. We will cover some of these applications in detail as we go deeper into the course. We are all used to questions as shown in the pictures here, like finding the point of intersections of two lines, finding the line of intersection of two planes, and so on and so forth. We would have studied these in high school. These are problems we can imagine, lines and planes living 2 or 3 variables or 2 or 3 dimensions. Most modern applications, however, deal with problems which have much higher number of variables. Our imagination is limited to 2 or 3 variables, 2 or 3 dimensions. Linear algebra gives you the tools and techniques to approach such problems in general, even with many variables, and builds your intuition in order for you to deal with these problems. Some notes on the prerequisites. I am not going to assume any background in linear algebra. We will start from the very basics. However, I will assume some basic familiarity with calculus, in the sense that you know what the derivative of a scalar valued function of one variable is, and so on and so forth, and we will pick up the rest from there. I have also included basic probability as a prerequisite. It's somewhat non-standard, but I have included that. One of the things that we do in this course is emphasize connections to other disciplines, and linear algebra's richness shows up particularly starkly when you bring in examples from probability. Properties like covariance chains, steady states of Markov chains, and so on and so forth require some basic understanding of probability. However, I am going to assume that the background required is very light. For example, you do not need to know central limit theorem or concentration inequalities and so on and so forth. As long as you know what the probability mass function is, what mean is, what variance is, what random variable is, what conditional probability is, you should be fine. Even if you not very familiar with these terms, I hope that does not deter you. You should mostly be able to pick up these as we go along in the course. Some notes on the style before we go on to the course contents. I am going to try to motivate each definition with examples. So almost every concept will be introduced by taking some concrete example. Some notes on the pace. I am going to go very slow so that everybody is able to follow. So the time per week may be higher than 2.5 hours on the average. While I try to motivate problems from applications, I hope that we do not sacrifice any mathematical rigor in the process. We may not, for example, cover all the topics a traditional linear algebra course covers, but whatever we do cover, we will do systematically. Now on to the learning roadmap. So the course is roughly in 3 parts. In the first part, I am going to go through the basics, vectors, matrices, matrix products, linear equations, rank, dimension, and so on and so forth. In the second part, we are going to discuss matrix decomposition. So we will only discuss QR decomposition, eigenvalue decomposition, and singular value decomposition. We will look at various results and applications of these decompositions. In the third part, we will see connections to various other topics. So we are going to study the principal component analysis, Markov chains, and page rank. We will also study gradient descent and stochastic gradient descent. However, we will limit our analysis to least squares objectives only. And we also study some basics of randomization in matrix computations, including Johnson-Lennon-Strauss and randomized least squares. A final note on references. So these are the textbooks suggested as references for the course. The first half of the course follows the first textbook in this list very closely. Up to the QR decomposition largely follows Professor Boyd and Vandenberg's text on Introduction to Applied Linear Algebra. The example based approach also draws heavily from this textbook. I have also listed some references which are useful for the rest of the course, including Strang's text and Horn and Johnson, matrix analysis, and Axler linear algebra done right. However, I will be providing lecture notes for each of the lectures in this course. I hope you enjoy the course. I look forward to active participation and happy learning.